Hello, this video is going to focus on sampling techniques and other things to consider when designing a statistical study. In order to motivate our sampling techniques, we're going to start with an example. This example came out of the textbook, An Introduction to Modern Statistics, which is linked in the notes. The images of the sampling techniques are also from this textbook. Suppose we want to consider the research question. Over the last 5 years, what is the average time to complete a degree for undergraduates at Duke University? The population here is all the people who have graduated with an undergraduate degree from Duke University in the last 5 years. And the parameter that we're trying to estimate is the average time to complete their degrees. We are going to need to pick a sample so that we can calculate a sample statistic and use that statistic to estimate our parameter. Remember that our sample will be a subset of the population who were selected for the study. Now the question is, how are we going to pick this sample? We're about to look at 4 ways we can do this. The first is we could use a simple random sample. This is probably like the golden ideal of sampling methods. A simple random sample of size n is a sample where each subset of the population that has size n is equally likely to be selected for the sample. Another way of saying this is that each element in the population has an equal chance of being included in the sample, and the elements are independent from each other. We could do this sampling. You could think about it like putting names in a hat, shaking them up and picking out names, or we could use a random number generator to generate the elements of our sample. Another way we could do the sampling is to use a stratified sample. With a stratified sample, first the population is divided into strata, which is just a fancy name for groups, and we're going to do that division based on some characteristic. Then a second sampling method needs to be used, usually a simple random sample, and it's used within each stratum to select the sample. So suppose we took all the recent graduates from Duke University and we split them up into groups based on their majors. We might want to do this because the different majors might affect the amount of time it takes to complete the degree, and so we want to make sure we have people represented from all the different groups of majors. We might create a group, stratum 1 might be the humanities, stratum 2 might be the STEM students, stratum 3 we might have nursing, stratum 4 engineering, stratum 5 business, stratum 6 social sciences. And then we would take a simple random sample and select 3 students from each one of those strata. The one benefit of a stratified sample is that you are guaranteed to have the different strata represented in your sample. A downside to a stratified sample is that the statistical techniques needed to analyze it are more complicated than using a simple random sample. A cluster sample also starts by dividing the population into smaller groups. In this case, the groups are called clusters. We then randomly select some of the clusters, and everyone or everything in those clusters is included in our sample. Usually these clusters are created based on locations, so like an apartment building, a neighborhood, a classroom, and then the researcher could just go to that area and collect a lot of data, maybe easier or for less money than if they have to run all over the city instead of just going to a single neighborhood or 2. In our example, let's suppose we had 8 different classrooms and we randomly selected classroom number 3, classroom number 4, classroom number 8. All the students who are in class 3, 4, and 8 are then asked to participate in our study. Another type of random sampling technique is a systematic sample. So a systematic sample is obtained by ordering the elements of the population, then you select a random starting point, and then you select every kth element. For example, every 10th element. So we have a list of 12 people here. We randomly selected to start with person number 2, put person number 2 into our sample, and then we just counted off the population by 3. We're selecting every third element here. So 1, 2, 3, 1. So now 5 is into our sample. 2, 3, 1. So now 8 is in our sample. 2, 3, 1, so on and so forth. This can be particularly good if people are already standing in a line, or if you're doing quality control for items coming out of a factory, for example. So we just looked at 4 techniques that should reasonably get us a representative sample. Now we're going to look at a few things that can go wrong with sampling. If we asked a graduate from a health-related field to find some friends to be in our sample, we might end up with a biased sample. This graduate might ask her classmates and end up with people who were also graduates of health-related fields. Our sample is thus going to be skewed towards health-related fields, and it will not be representative of the population. Another type of bias that we can run into is what's called non-response bias. This occurs when the response rate is very low. So suppose that we asked people in this inner circle here, we asked all of them to participate in our survey, but only 5 of them agreed. There might be a systematic reason that people are opting out of taking the survey, and that's going to make our sample bias. For example, people who engage in risky behavior, maybe they do drugs or drink too much alcohol or smoke or other types of risky behavior, they might not want to take a survey about their health and answer questions about their behavior. Another type of bias is volunteer bias, and that occurs when people opt into the study. So for example, people with more free time, people that are unemployed or retired, they might be more likely to take a survey than someone who's really busy. Also, someone who's really angry might go on to Yelp and leave a really bad review. If volunteers are getting paid to participate in the research, they might be more likely to be low-income people, and thus they're willing to participate in research to get paid. These are all ways that can skew who is choosing to participate in research. A convenience sample is a group of people or things that are easily available and accessible to the researcher. Some examples of convenience samples would be if you were to ask your friends and family to take a survey for you. If we go back to that example about Duke University, if we just showed up at a graduation ceremony and we found 10 students wearing a cap and gown, and we asked them how long it took to graduate, that would be a convenience sample. Convenience samples tend to be biased and not representative of the population. Another way we don't want to collect data is by using anecdotal evidence. Anecdotal evidence is collected in a haphazard way and is based on only a few cases, which may or may not be representative of the population. So for example, maybe you have a friend who has a cousin who took 7 years to graduate from Duke University. This does not mean that on average it takes 7 years to graduate. This is kind of a silly example, but people are more likely to remember extreme occurrences with unusual characteristics and then tell other people about them. So anecdotal evidence tends to stick out in our minds and can skew our perception of things. We have seen some ways that sampling can kind of go wrong. We've talked about bias sampling. And so to summarize, bias sampling systematically selects certain observational units, certain elements of the population, in a way that makes the sample not representative of the population. If an estimate is biased, so if a number estimate, if a statistic is biased, that means it has a systematic error in a particular direction. And note that bias is not the same as precision. A measurement is precise if the results are consistent with low variability. So if you're always getting the same answer, that measurement is going to be precise. If you're getting errors that are in the same direction, that estimate is going to be biased. And I'm going to show you a picture right now. So if we were shooting towards a target trying to hit the bullseye and all of our shots went right into the bullseye, then we would have an unbiased and precise shot. On the other hand, if all of our shots are close together, but they're all systematically to the lower right-hand side of the bullseye, then this is bias. It's still precise because the shots are close together, but there is a bias in our aim. If our shots are centered around the bullseye, they are unbiased. But as you can see, we're not a very good aim. We kept missing, and so it's imprecise. On the other hand, if, again, all the errors are in the same direction, in this case, they're towards the lower left, this is a bias aim, and because these are all spread out, they're imprecise. We're going to change gears a little bit, and we're going to talk about randomization in experiments. So the random assignment of patients to treatment groups or to control groups is called randomization. The control group may be given a placebo. A placebo is a pill with inactive ingredients that usually looks and tastes like the real treatment pill. A placebo might also be a type of treatment other than just a pill, but it doesn't really do anything. It's like a fake treatment. The reason we do this is that because people can experience the placebo effect. That is a psychological and physiological effect that makes people feel better when they receive a treatment, even if it's a fake treatment, because they believe it's going to help them. The word placebo comes from I will please, and it came from doctors giving people a treatment to make the people pleased rather than to actually treat them. Because receiving a treatment can make people feel better, whether or not it's actually an effective treatment, there's another technique that's used that is called blinding. In a single blind study, the subjects do not know whether or not they're in the control group or the treatment group. In a double-blind study, not only do the subjects not know, but the researchers who are interacting with the subjects also don't know which group the subjects are assigned to. This is so that the researchers don't act inadvertently in a certain way towards the subjects who are receiving the treatment versus the control. And also so that when the researchers are doing measurements, their knowledge of whether the people are in the treatment group or the control group doesn't affect their perception of the measurements. Proxy variables are variables that are used when the variable the researcher is actually interested in cannot be directly measured. So for example, researchers might be interested in the standard of living. That's kind of a vague topic. It's not very easy to quantify that. So instead, researchers might look at the per capita GDP of a country. Lurking variables are variables which are not being measured. A confounding variable is a variable that's associated with both the explanatory and the response variable in a statistical study. And that confounding variable is making it look as if the explanatory variable, is causing a change in the response variable, but really it's the confounding variable that's affecting both of the other two variables. This is a little confusing, but it's very important. So we're going to look at an example and then practice this more in class. For example, it might look to us like when ice cream sales increase, so do the number of shark attacks. Is that because sharks eat ice cream and then want another snack? No, what's going on here is that when the temperature is hot, people are more likely to buy ice cream. They're also more likely to go to the beach. and you can't be attacked by a shark on dry land. So it's really the temperature that's causing this apparent relationship between ice cream sales and shark attacks. This is a silly example, but we're going to look at some more examples in class. Because of confounding variables, we need to keep in mind that just because two variables are associated, like ice cream and shark attacks, that doesn't mean that one variable is causing the change in the other one. In statistics, we often say association does not imply causation. In general, we use experiments to show a causal relationship. And in general, we cannot use observational studies to show causal relationships. We can use observational studies to show that variables are associated, but we can't use it for that causal relationship because observational studies do not control for confounding variables. When the randomization is performed in an experiment, when people are randomly assigned to the control and the test group, and they don't get to pick which group they're in, that controls for the confounding variables by kind of like spreading them out evenly between the different groups. And that's why experiments can be used to show causal relationships, but observational studies cannot.